My name is Peter Sale. I'm a member of the Watershed Council and a member of the organizing committee. And I have a very special privilege this evening, and that is to introduce tonight's speaker. Before I do so, I've been asked to explain what the ELA is, because this has come up in conversation during the day. The Experimental Lakes area is a institution that has been run for 40 plus years by the the Department of Fisheries and Oceans. It consists of a large area with a number of lakes. I don't know how many lakes in northwestern Ontario, plus some infrastructure and some staff. And it has been responsible for some really important ecological studies, chiefly of an experimental nature, frequently involving manipulations of whole lakes. Some of the things that have been done at the ELA have informed us of the relative importance of nitrogen and phosphorus in stimulating algal blooms, for example. And that led to the banning of phosphorus detergents in Canada. Some of the other studies have related to acid rain, and those studies were instrumental in developing the treaty between Canada and the United States on acid rain, which led to the kind of improvements that made it possible for the rehabilitation of submarine that we heard about earlier on today. The ELA has 40 plus years of environmental data, which is an immensely valuable data store, which tells us about how our environment is changing and tells us very clearly how climate change is changing that part of Canada. This is why it's important. It's not important because scientists get to go and do really neat experiments there. It's important because it is a long-term environmental agency which has provided valuable information and can continue to provide valuable information for Canada and the world. There is nothing like it anywhere else on Earth. And our government has decided we don't need it because we could save somewhere between $600 and a couple of $1 million a year, which is a trivial amount in the Canadian budget. They have decided it's so unimportant they've not even provided a public report of the fact that they're closing it down. That's why a number of people at this meeting are concerned about it. That's why everyone at this meeting should sign that petition and take the initiative to individually write to your Member of Parliament, the Prime Minister, and the Minister of Environment about how wrong this is. Judy, did I explain? Good. Okay. I've done it. And as a scientist who has seen the withering away of Canadian environmental science, I feel really strongly about this. Anyway, shifting gears. It's my privilege to introduce tonight's speaker. I first met Tom Lovejoy at a conference somewhere in the mid-'80s, and I confess I can't remember when, which I attribute to age, but I think it was at Syracuse, and it doesn't really matter because I already knew about him as an ecologist myself. As a student of ecology. I knew about him because of one photograph. A strange photograph which has appeared in millions, well not millions, hundreds of textbooks. It is on the web right now. It is all over the place. It's been in National Geographic. And it is a photograph of this funny looking square of rainforest surrounded by cleared land. And that photograph is a part of one of the biggest ecological experiments that was ever run. Ecology is a kind of a funny science. You can't bring ecology into the lab very easily. So if you're going to do experiments at all, you have to do them out in the field. And mostly ecologists do experiments that are too small because they don't have enough money to do anything big. Well, the people who did this experiment worked with the people who were clearing the land and convinced them to make a series of exceptions to their clearing and to produce these beautiful squares of forest of different sizes, because they wanted to answer the question, how small can a rainforest be and still be a rainforest? How small can it be and still capture the biodiversity and the ecological processes which make it a rainforest? That's not a trivial question. And that question can be applied to every kind of habitat we have. And that question is intimately tied up in the question of how big does a protected area need to be? And if you've got 5 small ones, is that okay when you could have one big one? That was an important experiment. It began in the late 70s, and the person who began it, or the person who led the team that began it, because it wasn't a one-person project, was tonight's speaker, and that's Tom Lovejoy. That experiment is still running. There are still scientists getting results from that experiment that are informing us about how forests work. And it's a beautiful example of what is possible when scientists do things creatively. Now, Tom Lovejoy began his career with his education at Yale. He went on to doing this experiment, but he went way beyond there. He became an advisor to the World Bank. He became an advisor to the World Wildlife Fund. He became an advisor to, and get this for political correctness, Presidents Reagan, Presidents Bush, President Clinton. This guy has been involved in science and policy throughout his life. And he's the guy who actually came up with the term biodiversity and talked about biodiversity loss in the context of rainforests right from the beginning. He is currently a professor at George Mason University. He's the former director of the Heinz Center for Biodiversity at George Mason University. But he has a long and illustrious career, and we are so fortunate to have him here tonight. I should tell you that when we invited him, we knew he had a tight schedule, a busy schedule. We didn't know how busy. Tom Lovejoy flew into Toronto at 6 o'clock this morning. When he finishes talking this evening, he's being driven down to Toronto so he can fly out tomorrow at 6 o'clock in the morning. When I say we are privileged, we really are, and we owe him a big thanks for coming here, talking to us tonight. And he's going to talk to us about a wild solution for climate change. I ask you to join me in welcoming Dr. Tom Lovejoy.
So thank you, Peter, so much for that very generous introduction. It has been a real delight to be part of today and sense all the energy and the engagement of everybody here. Just quite special, and the mention of acid rain reminds me that John Heinz, the former senator from Pennsylvania, for whom the Heinz Center is named, was very interested in, together with his colleague Tim Wirth, in how market forces could actually work for the environment. And he was specifically responsible for introducing the sulfur market in the Clean Air Act of 1990. So, interesting example of trying to take a practical step for a better environmental outcome. So we had a lot of discussion today about hippo. And I just thought, for those of you who don't understand a lot about the ecology of fresh waters in Africa, hippos, real hippos, are extremely important in terms of the productivity of fisheries in East Africa, because basically they feed on land and they defecate in water and basically fertilize the aquatic ecosystem. And it's a very interesting thing to observe, because the tail of a hippo is not much bigger than that. But when the feces come out, it goes like that. And as far as I'm concerned, it's the original shit hits the fan. So, now let's see if we can be faintly serious. So what I want to talk to you about tonight is the issue of climate change and how it interacts with the biology of this planet, and how the biology of the planet can actually help us address climate change. And of course, we're having this discussion barely a week before the nations of the world are returning to Rio de Janeiro 20 years after the Earth Summit, which gave birth to two conventions, one on biological diversity and one on climate change, both of which are intimately involved in the topic this evening, and returning hopefully to advance the agenda more constructively and further than it has gotten so far. So, in 1896, the Swedish scientist Arrhenius asked an incredibly important question. And that question was, why is the Earth a habitable temperature for humans and other forms of life? And why is it habitable? Why isn't it too cold? And the answer was greenhouse gases, building on some previous work, but in particular around carbon dioxide. And he actually was so accomplished that with pencil and paper, he worked out what doubling pre-industrial concentrations of CO2 would do to the Earth's temperature, and it came out almost exactly where the big fancy computer models still predict it would come out. What Arrhenius did not know was much about the previous history of the climate on the Earth. There had been obviously awareness of the advance and retreat of glaciers, but he had no sense of the kind of temperature record that's represented here, and in particular that the last 10,000 years have been a period of unusual stability in the Earth's climate. And that, of course, includes all recorded human history, a significant piece of unrecorded human history. It includes the origin of human settlements, the origins of agriculture. It basically makes the point that the entire human enterprise is based on the assumption of a stable climate. And in that same 10,000 years, of course, all ecosystems have been adapting to a stable climate. And that is something that we're busy changing, pumping CO2 in the atmosphere to levels that haven't been seen for long periods of time. And the Earth's climate system is responding. We're now somewhere between 0.8, 0.9 degrees warmer than in pre-industrial times, and with no sign of any slackening, are continuing to add greenhouse gases to the atmosphere at rates which are worse than the worst case scenario of the last projection of the Intergovernmental Panel on Climate Change. So what I'm going to spend this evening talking about is a little bit about climate change but not a lot. And we're going to be talking about how the natural world is responding to this climate change. So obviously a big piece of it is around the solid and liquid phases of water. This kind of scene is something that here in Canada you are much closer to than we are in the United States. But obviously with the annual expansion and retreat of ice in the Arctic Ocean, there is a serious trend going on. And we are seeing similarly lakes freezing later in the autumn and ice breaking up earlier in the spring. And in many parts of the world, glaciers are in retreat, and Glacier National Park will soon be that only in name. And in the tropics, where there are glaciers at high altitudes, like here in Kilimanjaro, all tropical glaciers are retreating at a rate that they will be gone in 15 years. Another of the physical changes involves sea level rise. This is no longer a matter just of thermal expansion of water. It's also rising because of melt of ice on land as opposed to ice that's floating in water. So on the eastern shore of Maryland, the Blackwater National Wildlife Refuge, through a combination of sea level rise and natural subsidence of the land, is well on its way to becoming a national marine refuge. There's still a little question, but not a big one, about the increased frequency of intense tropical storms. The debate is still a little open, but the trend is pretty obvious, and extreme weather events, I think, are a general phenomenon almost everywhere in the world. There's absolutely no debate about the increase of wildfire in the American West and Southwest because of milder summers and earlier snowmelt. This has essentially become part of the annual news cycle. But the rest of this evening I want to talk about how the biology of our planet is responding to this climate change. And so what we're seeing, and I'm sure you all are familiar with local examples, and I would love to learn about them. I always like to add new things to this talk. But one of the things that's being seen, like here in New England, is a change in the timing of life cycles of plants. So lilacs are blooming earlier in New England, United States, New England. And at the Royal Botanic Garden at Kew, there are a whole variety of plant species whose blooming time is now earlier. And it's not just plants that are changing their annual cycles, it's also animals. So tree swallows are migrating earlier, nesting earlier, laying eggs earlier. And more important in a way, species are beginning to change where they occur. So the Aedes checker spot is one of the two best-known species of butterflies in North America, and it has clearly been moving northward in latitude and upward in altitude in response to climate change. Similar kinds of things have been observed with butterflies in Europe. And most recently, I ran across an example in the Sierra Nevada of the effects of climate change. Had the great treat of waking up on Earth Day in Yosemite Valley, but in the process learned that the snow no longer falls in the Sierra down to 3,000 feet above sea level, but rather goes only to 4,500 feet, and the ponderosa pine, which actually depend very much on that winter snowpack, are dying out in that belt where the snow no longer falls. So the National Arbor Day Foundation, which is hardly some wild-eyed environmental extremist terrorist organization, but rather about people who just like to plant trees literally found it necessary to publish a new hardiness zone map to guide their members in choosing tree species that they could be successful in planting where they live. And the changes are occurring not only in the land, they're occurring in the oceans. So plankton distributions are changing, fish distributions are changing. In the Chesapeake Bay, the great estuary of eastern North America, the seagrass turns out to be, eelgrass turns out to be very sensitive to temperature. It has a strict upper limit, which it will not grow above. So the southern boundary of the seagrass beds, eelgrass beds in Chesapeake Bay has been moving steadily northward year after year. So these changes are not only in the Arctic regions, not only in the temperate regions, we're also seeing things happen in the tropics. So here we're looking at the legendary cloud forest of Monteverde in Costa Rica, an extraordinary place. And here the impact is not so much in terms of a change in temperature, but rather here the impact is about the altitude at which clouds form. So there are increasing numbers of dry days in Monteverde, which is a really serious issue for an entire ecosystem which depends essentially on condensation from clouds for 95% plus of the moisture. And we're also seeing decoupling events. Maybe somebody here will have a photo that can actually show what I was looking for when I put this together. But decoupling events are when there are two tightly timed elements in nature, one of which happens to use a day length cue and the other uses a temperature cue. And that's what we're seeing here, because it's now a frequent event to see snowshoe hares in their white winter pelage, no longer against a snow background, but against a non-snowy background where they become very vulnerable to predators. And another really interesting example involves the black guillemot, a seabird which, amongst other things, nests on the northern Arctic Ocean shore of Alaska. And black guillemots feed on Arctic cod. Arctic cod sort of hang out at the edge and just underneath the Arctic Ocean ice. And so the adult guillemots fly to the edge of the ice to feed on Arctic cod and bring them back to their nests for their young. So this has become a longer and longer journey for the black guillemot adults to make every year, and some of these nesting colonies have now failed as a consequence. And this totally incomprehensible slide, which I would take points off if any of my students ever produced one like it, is actually to make the point that this is no longer a matter of sort of individual anecdote or individual story. This is now statistically robust. Wherever you look in the world, there are ripples of change in nature. Nature is on the move. So these are relatively minor changes, things which nature seems to be able to sort of cope with. The issue is, what is it really like going forward? And so that's what I will spend part of the remainder of this talk on, and then finally I'll talk about what can we actually do about all of this. So when one knows a lot about the biology of a particular species like we do with sugar maple, it's possible to actually project where their requisite climate conditions will occur in the future. So the good news for Canada is that at double pre-industrial levels of CO2, you will have sugar maple, and autumn foliage and maple sugar and maple syrup, and the United States will not. Similar kinds of changes in tree distributions have been done, projected in Europe. Similar kinds of results. And a lot of this is not just about temperature, and that's a really important point to make. Because if you stop and think about it, the two most important physical factors for terrestrial organisms are temperature and moisture. Or for aquatic organisms are temperature and pH or acidity. And all of those are changing. And they're also changing at a time when there are other stresses put on particular ecosystems and habitats. So here you're looking at the consequences of climate change-driven drought plus habitat encroachment and destruction in Chad, which has basically brought Lake Chad to about 5% of its original extent. This is going to have consequences for freshwater species, particularly cold water loving species like trout. It will also have consequences for species which live in high places, which will be retreating essentially upward, trying to track their required climatic conditions. This is the pika, which occurs in the United States in maybe a dozen populations on different parts of the Rocky Mountains. Marvelous little animal related to rabbits with great biology that I don't have time to go into. But basically, species like the pika will be moving upward, trying to track their required climatic conditions until ultimately there's no further up to go. So this is a projection you're going to see of the endemic bird and mammal species in the rainforests of Queensland and Australia. These are species which occur only in these rainforests. The intensity, the color reflects the number of those species. As you can see, with increasing climate change, it becomes a very inhospitable place for those species. And ultimately, if we keep going in that direction, they will be lost. So another category of species which are seriously going to be impacted are those that live in coastal regions because of sea level rise, and some will manage to deal with that, and others will not. And there have been some imaginative sort of conservation practices, sort of allowing these kinds of species to retreat inland as that process goes forward. But those living on low-lying islands like the Key Deer and the Florida Keys are going to be extremely vulnerable because at a certain point their islands will simply be underwater. But it's not just low-lying island species that are in this group of first to be impacted by climate change. It's mostly any island species because as the climatic conditions no longer are favorable to the species on islands, even if they're higher, it basically becomes a very inhospitable place for island species. So island species as a class, together with high altitude species, are particularly early vulnerable in all of this. And of course, any species, and this is the last place in the world I need to go into detail on this, but any species with a natural history which is tied to ice is clearly very vulnerable. And I'm sure there are people in this room who can sort of match my expertise on this by a factor of 100, so I'm not going to go into any detail. So, on top of all of this, as there is more climate change, the kinds of impacts become more complicated. And so if there's one message to get out of this evening, it is that the more climate change there is, the more difficult it is to actually counter-manage, to try and secure the future of elements of biological diversity. So there are about 4 major complications, one of which involves what humanity has done in managing landscapes around the planet. And if one thinks about it, of course, climate change is certainly not new in the history of life on Earth. And glaciers came and went, particularly in this part of the world, in the northern part of the United States, and parts of Europe and Eurasia. And not a lot of biological diversity was lost in the process. What is different between then and now is the major transformation of landscapes by human action. And this is the classic illustration from the original paper on island biogeography back in the 60s. And it shows what's happened to natural habitat in one township in Wisconsin, from the upper left to the lower right. But that kind of pattern is basically universal around the planet. It rarely is habitat destruction something that just takes half of a particular kind of habitat and leaves all the rest in one big block. It usually is accompanied by fragmentation, and that basically turns the landscape into an obstacle course as species try to move and track their required climatic conditions. Now, this is a pretty easy one to address. And, you know, what we heard about this afternoon in the Corridor Project in Quebec is a good example of just consciously trying to put connections back into the landscape. Similar kind of thing actually is happening in the city of Chicago, the Chicago Wilderness Project. So putting connections back into the landscape makes it a lot easier for species to actually move and adjust as the climate changes. But a more difficult problem with increasing climate change is that ecosystems don't actually move as a unit. They actually move as individual species, each at their own rate and in their own direction. So here we're looking at what happened with 3 mammal species, 2 tree species, and an insect after the retreat of the last glacier in Europe, and you can see there's no common pattern. So basically what happens is the individual species will move, and essentially the ecosystems will disassemble, and the surviving species will assemble into new ecosystems, which are actually very hard for us to imagine. There's also the issue that despite the fact that our computer models are all about linear and gradual change, that's not the way climate change always occurs. So there have been lots of abrupt change, and in fact that initial temperature graph I showed you showed a lot of abrupt change. This is the global conveyor belt that moves heat around the planet and the oceans. It's been known in geologic time to shut down. We're also beginning to see abrupt change in ecosystems. And certainly you've seen it here in Canada. In fact, the entire coniferous forests of western North America, from southern Alaska all the way down to Colorado, are seeing massive changes in the forests. So I'll just take you through time sequence of this happening in British Columbia. And basically we're looking at a change in which balance is tipped in the favor of the native pine bark beetle. And this will take us up, I think, into the earliest part of the 21st century. But you can see the little outbreaks are getting to be more extensive. And even when it gets to 1985, when there was actually a quite cold winter, it doesn't knock it that far back. So basically, all the way down into southern Colorado, there are vast areas of the forests of western North America in which essentially 70% of the trees are dead. And this is a huge challenge for management of these forests. It's a fire issue, a whole series of these things, and nobody really knows what will come of them all. So that's the kind of an abrupt change that we're beginning to see in ecological systems. And this is, the point of abrupt change in ecological systems is a really important point because we're already seeing some. The biggest, which we're seeing so far, I think, involves tropical coral reefs, which all looked like this when I was in graduate school, this extraordinary technicolor world, high diversity, high productivity, extraordinarily important for the 1/12 of humanity which depend on tropical coral reefs. And starting in 1983, we began to get a different kind of tropical coral reef response to the creeping increase in global temperatures. And it turns out it doesn't take a lot of increase in water temperature for a very long period of time before it affects the fundamental partnership, which is the heart of the tropical coral reef ecosystem. The partnership between a coral animal and an alga. And when you just get just a little bit of heat, just a little too long, the coral animal expels the alga, and you get what are known as bleaching events. And the entire system crashes. The technicolor world becomes black and white. The productivity and the diversity crash, and the benefit to local communities plummets. So that is a second example of an abrupt change in ecological systems that we're already seeing, and with increasing frequency year after year. And then finally, there are even larger scale changes, which I call system change for lack of any other obvious way to call it. And one of these involves the extraordinary way in which moisture is generated and moves around the world. This would make such a great screensaver. It goes hour by hour for a whole year, and I won't take you through it all, but look over on the far right, and you'll see that moisture is coming off the tropical Atlantic and entering the Amazon basin, and then it's recycling in the course of moving towards the Andes, where it finally hits the high wall and produces a lot of rain in the Amazon river system and a bunch of other things. There has long been a concern about, how much deforestation might cause that to degrade as a system which keeps the Amazon in tropical rainforest. So the first computer models, maybe 6 or 7 years ago from the Hadley Center, predicted that at 2.5 degrees of climate change, you'd actually get that system breaking down to the point where you would have dieback in the southern and eastern Amazon, and they redid it maybe 3 years ago, and it turned out that would happen at 2 degrees. The most recent run of that model showed absolutely no effect at all. And then maybe 2 to 3 years ago, the World Bank put $1 million into a study modeling the effects of climate change, deforestation, and fire all together, which had never been done, and suggested you might actually have a tipping point to that dieback at maybe 20% deforestation. Well, I tend to think you need to take that all pretty seriously, but, setting that aside for the moment, in 2005, there was the greatest drought in the recorded history of the Amazon, which is on the right. And 5 years later, there was an even greater drought. So are those previews of the effects of climate change affecting this system? Who knows, but I don't think it should be brushed aside as one thinks about managing the climate or managing the Amazon. So obviously, if that happens, there's a big impact on biological diversity, there's a huge release of carbon in the atmosphere, and just an amazing impact on the people who actually live there. Basically, I think we are moving up to the point where we might actually be affecting some of the critical thresholds in the way the Earth system works. And we don't know a lot about that, or them. But one thing is pretty clear, it doesn't make a lot of sense to be trying to sort of find out what actually tips those systems by tipping them. That's just not the experiment we want to do. So another huge system change was totally ignored until about 2005. It went right by every single one of us. It's really sort of embarrassing. All the people who worried about CO2 in the atmosphere, would always say, we're so lucky that about half of the CO2 gets absorbed by the oceans. Nobody had sought to think about their basic high school chemistry and realize that some of that might turn into carbonic acid. And so that, in fact, is what is happening in the oceans today, or as a consequence, 30% more acid than in pre-industrial times. The pH unit is only 0.1, but it's an exponential scale, so that's a serious change. And why should that matter, other than the shocking notion that we could actually make that big a change in the chemistry of the Earth system? It's because there are tens of thousands of species which depend on a carbonate equilibrium to build their skeletons or their shells. And some of them are, spectacular things like coral reefs or giant clams, but then there are a lot of little guys, like this one, which are at the base of food chains. And this is what is known as a sea butterfly. It's a tiny little snail. As you can see on the right, what normally would have been sort of the foot of the snail moving around has been modified to create sort of two wings. And there is one of these sea butterflies. And basically that allows it to keep up in the water column. And they are in the gazillions at the base of food chains off Alaska and in the North Atlantic. And there are already changes being observed because of the increased acidity of the oceans in their shells. So, I'm going to take you quickly through what ocean acidity might mean for tropical coral reefs. And the thing to really look at is, I may not do this right, is this right up here. So this is pre-industrial levels of CO2. This is a little lower than, go back to 380. This is a little lower than we are now. Thank you very much. This is where the negotiators are talking about stopping at. Not great for tropical coral reefs. And then finally, at double pre-industrial levels, the oceans are basically not hospitable to tropical coral reefs. So all of that over time has led me to the conclusion that this 450 part per million 2-degree target that the negotiators are talking about actually is too high. 2 degrees is too much for ice systems, it's too much for ecosystems. And I will have a little bit of a solution here, so don't panic. But the last time the world was 2 degrees warmer, the oceans were 4 to 6 meters higher. I mean, what more do we need to know, right? I mean, it's pretty simple and straightforward. So the issue, let's go back. And this is just the Royal Society making the point that at levels over 350 parts per million, it's not going to be great for tropical coral reefs, a point I made in a different kind of way. So a small number of us have come to the conclusion that instead of 450, we should be talking about something that's lower than that, perhaps 350, ideally, 280, the original, would be the one to head for, but 350 seems like it might be at least reasonable. And so then the issue becomes, what do you do about that? And it's really hard when you confront the fact that if you want to stop at 2 degrees, global emissions have to peak in 2016. If you want to stop at 2 degrees, which I've already said is too much. What is it? Jumpy. So then the issue becomes, what do you do about all of this? And there are things that can be done. They're not widely known at the moment, but I think they're beginning to get some traction. So this is Dr. Planet. He's made the diagnosis that 2 degrees is too much. So what do you do about it? What is his prescription? And there are a bunch of things to do in modifying conservation strategies, a bunch of things to do limiting greenhouse gas concentrations. So the conservation strategies are pretty obvious. We already mentioned putting natural connections back into the landscape. Sounds like some of that's already happening here in Canada. Another is just to minimize the other stresses on ecosystems to avoid negative synergies. There's obviously a huge energy agenda, but that's not my expertise. And then there's a really interesting piece of emissions, which you probably all know about, but most of the world doesn't pay much attention to, which is that even today, a significant fraction of annual emissions comes from the destruction of modern ecosystems, particularly tropical forests. Maybe, I would guess, no longer 20%, but in absolute terms, still a significant number, maybe pushing 15%. And so one of the things one can do is actually protect a lot of biological diversity by avoiding the destruction of those ecosystems. And this is the basic equation that we have to play with, because I think we've arrived at the point where we actually need to consciously think about managing the planet and the climate system. So in any given year, about 5 times the amount of tropical deforestation emissions is emitted by burning fossil fuels, and about half goes in the atmosphere, and the rest is divided between the oceans and the land. So the idea is, how can you start playing with this equation? So maybe you could even reverse one of those arrows. And it becomes really important because of the length of time greenhouse gases stay in the atmosphere. It's 100 to 1,000 years. The longer they're there, the more they are actually contributing to the warming of the Earth. So then we come to sort of the wilder idea here, the wild contribution to climate change, which is looking at ways to actually pull CO2 back out of the atmosphere long before it has generated some of the climate change and the consequences that might otherwise be the case. And it turns out that over about 3 centuries, there's been a lot of CO2 going into the atmosphere from ecosystem destruction. And the power of biology in all of this is actually considerable. So twice in the history of life on Earth, there have been screamingly high levels of CO2 brought down to pre-industrial levels. The first time it came down was with the arrival of plants on land. And it wasn't just plants, it was also soil formation and all the biodiversity in the soil involved in generating soil. The second time was with the arrival of modern flowering plants doing the same thing but more efficiently. So the power of biology in all of this is considerable. It's fact. It's historical, geological fact. The issue is that we don't have tens of millions of years for that to happen in any natural kind of time span. So the really interesting thing is maybe something like 40% of the excess CO2 in the atmosphere actually comes from 3 centuries of destruction and degradation of modern ecosystems. So it should be possible to actually do planetary scale ecosystem restoration and bring a significant portion of that CO2 back into living systems. So this is my original little sketchy diagram suggesting this about 5 years ago. And the REDD up there is just about reducing the emissions from deforestation and degradation. That's a technical UN term. But the bigger potential impact is ecosystem restoration. So I think there's actually no question about it. Checked it around with IPCC and the rest. There's at least 50 parts per million that could come out of the atmosphere by planetary scale ecosystem restoration. And that's the difference between 350, which is sort of safe, and the 400, which has recently been measured in various places in the Arctic. Global average is 395, but the first readings of 400 have showed up in the Arctic. And the last time, by the way, this planet had 400 parts per million was 800,000 years ago. Anyway, the difference of 50 parts per million is something that it could actually be done by ecosystem restoration over a 50-year period. And so it would be 500 million tons a year through reforestation and managing forests more effectively from this perspective. Another 500 million tons a year by restoring grasslands and degraded grazing lands with the great benefit of better grazing. And a third 500 million tons a year through managing agroecosystems in ways that will encourage them to build up carbon in the soil rather than leak it. And the more carbon there is in soil, the more fertile the soil is. So there are ancillary benefits from this kind of approach. So, and we can do all of that and still worry about feeding the additional 2 billion people this planet is going to have to feed, and who knows, maybe a bit more. But it's possible to do all of that without encroaching on the agricultural potential of the planet. So I think in the end, if we start thinking about managing the planet as a system, we can literally deal with a really important part of this climate change challenge by re-greening the emerald planet and using the living planet to make it more habitable. Thank you very much. So anyway, the good news here is we don't all have to go to the nearest bar and never reappear again. There are things you can do.
first of all, this was an amazing presentation. I'm very glad you came down here. And I was wondering when you coined the term biodiversity.
So that was what I actually was the first use was the term biological diversity.
Yeah.
And that was 1980.
Okay.
And then it got contracted into biodiversity by somebody else in 1987.
Thank you very, very much for your talk. Very, really outstanding. You've obviously been tremendously influential with many governments of different persuasions over many years. We have some issues here in Canada where many of us would like to be much more persuasive and influential with some of our governments. I was wondering if you could just speak a little bit to how to be persuasive and influential with governments.
Well, you do have a challenge here from what I hear. It's not that we haven't had some of our headaches in Washington, that's to be sure. And actually, sometimes you take advantage of just lucky misperception. So one of the things I got to do was to brief John Howard when he was Prime Minister of Australia in his Science and Technology Innovation Council on Biodiversity. And as I left the cabinet room, he politely got up to thank me, and I said something to him, and he lit up, and and then I left the room. And for years afterwards, people wondered, what kind of hold did I have on John Howard? And all I said was, Tom Cruise said to say hello. So they thought I was really influential, right? There are a fraction of elected officials who are just impenetrable. But there are others, if you don't sort of go for the jugular, you try and figure out what they're thinking about, you might actually get somewhere. So I think you're quite familiar with the difficulties on these issues with the Republican Party in the Congress of the U.S. at the moment. I did a presentation for an Aspen Institute study tour in Brazil in early April, and there was only one Republican who went on that trip, right? And he'd already announced that he didn't believe in climate change the day before I got there. But he actually read my piece and read a little bit of this idea of using biology to sort of pull CO2 out of the atmosphere, and he said, I think I could be in favor of that, right? So, it's just look for the openings as you can find them, and it never hurts to have somebody else to make you look like the good guy because they're sort of being difficult. And Russ Train, who was the first head of CEQ in the United States and the second head of EPA, once said that David Brower made him look reasonable. David Brower said, Russ Train makes me look unreasonable. But the point is sometimes the more extreme environmental point of view will actually make what you might want to do seem like centrist. And of course we understand that it's not so much an issue of how something looks, and we know we're all sort of looking at this through scientific eyes one way or another. We know what needs to be done. But some of that higher social primate behavior is a really important way to sort of think about infiltrating. And sometimes you just need to come out strong and just utterly oppose and be hypercritical. But other times, at least somebody's got to be trying to talk with the other side. And it's gotten harder and harder, and I don't want to belittle it at all. I mean, it drives us nuts in Washington. I said to somebody this afternoon that the congruence in the U.S. Congress of those who don't believe in climate change and those who don't believe in evolution is actually creating the greatest experiment in the history of life on Earth to prove natural selection. Sir.
Thanks very much. It was informative and tremendously interesting stuff. I think I'm an economist. I always like to admit that in front of this crowd so people can throw buns at me. But for all of the compelling numbers that you've got, I appreciated that you came up with some solutions at the end because it's not all doomsday. But I think until it can be turned into the real part of the mainstream conversation, which is so what do we do about it, and what do we do about what are the solutions related to the economic imperative? In other words, how do we make our economies thrive, and how do we make our societies, how do we deal with all the extra people, and how do we feed everybody, and where's all the water going to come from? The solution part of it's often where we are left lacking. So I'm curious about how you make the leap from what's obviously a robust amount of science related to what the geological history is telling us about where carbon is going in the atmosphere, how that's changing our climate and our biodiversity, but how then we do something about that in terms of how we conduct ourselves as a race and how we feed ourselves and manage our water and our food systems, because making the leap from biological and chemical science to the part about feeding ourselves and just conducting ourselves, there's another whole aspect, and this is part of Peter's discipline here, but how do we turn that into an economic discussion where we can actually figure out how to deal with the problematic species, which is all of us?
So economics and how it's practiced is central to the solution, without any question at all. And any solution that doesn't sort of embrace the notion of essentially a dignified future for all people is not going to get anywhere either. And so, I could make what sounds like a flip statement, but actually isn't. I think we need a redefinition of the quality of life. I'm old enough to remember, how my parents were not impoverished by any means, but the sense of frugality that they had about the use of resources that came from rationing in the war and the Depression has been pretty much lost. I could go on about that at length, but in any case, I spent a lot of time talking with economists. I actually just got the second go around to look at Bill Nordhaus's new book on climate change. Pavan Sukhdev and his work on the economics of ecosystem and biodiversity and the role of the corporation, I think, is quite thoughtful and progressive. And what's also interesting is I see in the for-profit world, in major multinationals, a sense that they actually have to take these things quite seriously. So you might think of Coca-Cola as a company that's only about making everybody obese. Well, in fact, they don't only make Coca-Cola. They're very concerned about water quality. They're very concerned about, you probably saw it, that they did a little campaign for polar bears at the end of the year, Save Our Arctic Home. Their feeling was their real expertise is in branding, so they want to bring it to this kind of issue. And a whole bunch of corporations that you would might not think at first blush would be interested in these things at all are, like caterpillar. I don't know what the number actually is, but every new Caterpillar machine is probably 80% remanufactured. I mean, it's quite extraordinary. So I think the corporate world can actually help us a lot in all of this. But your point is very well made. Until we're able to bring some of these important values into how economic decisions are made, we're only going to be able to get so far. Yes?
It's a very hypothetical question, but if climate change wasn't occurring and all its associated effects, how much trouble do you think biodiversity and ecosystems would be in, just based on things like pollution, habitat fragmentation, and so on?
Well, no question that biodiversity is, at this point, biodiversity isn't being hugely impacted by climate change. We're just seeing the signals of where it's going. So all the problems that you're seeing mostly come from all those other activities. And I think a really important point to be made, and it gets made very rarely, is all that biological diversity is essentially an enormous living library of pre-tested by evolution solutions to all kinds of environmental problems and biological problems. So some of the things that we're going to need in agriculture or medicine or whatever else have already been worked out in the process, and they're just sitting out there waiting for us to learn about them. So I could tell you, for example, and I don't have the time to the detail, that probably 30% of the people, or at least of the older people in this room, are probably being treated for hypertension from something that's based on the biology of poisonous viper in the New World tropical forests. And the benefit to humanity from the Human Genome Project it's almost beyond calculating. All that depends on an enzyme from a bacterium at a Yellowstone hot spring. So all those kinds of benefits, when we get them, we treat them as free. We shouldn't treat them as free. We should find a way to build that into how we manage ourselves and the planet.
I was wondering if you could, so the boreal forest in Canada is a great potential for your plan, in the sense of avoided deforestation in particular. And I was wondering if you could say a few words about that in light of the fact that RED is not, going to be applicable mostly to temperate forests. It's really directed at tropical forests, but also the alternative plans that our government has for gaining our prosperity through natural resource exploitation in boreal forests, and sort of how to reconcile some of those competing things with being able to undertake avoided deforestation in that biome.
So I wish I had a magic answer for you. I don't, in part because I don't know the full sort of politics and everything that's going on around that. But I think it's abundantly obvious that hopefully sooner rather than later that we're going to have to put some price on carbon. And the minute you do that, biological carbon begins to have a value that it doesn't at the moment. And my only concern has always been that to value a forest only for its carbon is like valuing a computer chip only for its silicon. So we need to be really thoughtful about how we approach that.
I'd like to ask all of you to join with me in thanking Tom Lovejoy. For finish, so you're going to have to do it again after I finish. I was going to say we have a small gift for him, and it's particularly appropriate because of his comment that Canada is apparently going to have sugar maple into the future, and his country isn't. Because here's some genuine Muskoka maple syrup, and it's a very small gift and a very small thank you, but we really appreciate you coming up and talking to us today. Thank you very much.